This discussion centers on the paper titled Particles as Emergent Structures, a Unified Framework for Deriving Particle Properties from Spacetime Modulation Dynamics, authored by Christopher Young. The paper develops a comprehensive mathematical framework that reconceptualizes elementary particles not as fundamental point-like entities embedded in spacetime, but rather as emergent, stable resonance patterns arising from coupled dynamics of spacetime itself and an auxiliary modulation coordinate, or AMC. The purpose is to derive particle properties such as mass, charge, spin, and quantum numbers purely from first principles, without invoking free parameters or fine-tuning, thereby addressing long-standing foundational issues in physics. The paper begins by addressing a central challenge in contemporary physics, the persistent dichotomy between the geometric description of spacetime in general relativity and the quantum field theoretic description of matter. Traditional approaches treat particles as independent objects existing within spacetime, leading to difficulties in unifying the two frameworks. The AMC framework proposes a paradigm shift by introducing an additional dynamic coordinate, the modulation dimension, which couples to spacetime and allows particles to be understood as specific oscillatory modes, stable resonance patterns, within this extended spacetime modulation manifold. This idea parallels and extends previous theoretical efforts such as the amplituhedron framework by Arkani, Hamed, and Trinka, which seeks geometric foundations for particle interactions, and Carroll's view of quantum field theory as a different language describing everyday physics. The AMC framework advances these perspectives by providing explicit mathematical derivations of particle properties, explaining why these properties emerge with the observed values rather than treating them as axiomatic or phenomenological inputs. At the core of the framework lies a unified field system described by a master field denoted as E, which depends on spatial coordinates x, time t, and the modulation coordinate Var-epsilon. This master field decomposes into a spatial modulation field, capturing the elastic oscillatory character of spacetime, and a temporal modulation field encoding quantum phase evolution. The system is mathematically represented as mathcal u xt Var-epsilon equals phi text spacetime xt Var-epsilon plus theta t Var-epsilon. The dynamics of this field are governed by a generalized modulation-based field theory equation, an integral over four-dimensional spacetime including the modulation dimension, incorporating terms for temporal and spatial energy, potential energy, and harmonic resonance. A universal weighting function with precisely determined coefficients arises from entropy-resolved resonance profile computations, serving as a selection mechanism that dictates which resonance patterns form stable particles. Elevating the modulation coordinate, Var-epsilon, to a fully dynamic dimension leads to a wave equation extended by modulation space curvature terms, stabilization potentials, source currents, and harmonic drives. This extension not only enriches the mathematical structure, but is physically motivated by phenomena such as non-commutative derivatives involving Var-epsilon, indicating its intrinsic physical significance. The resulting field equation can be summarized as frac partial phi partial t squared 9 nabla 2 phi plus ln 2 frac partial 2 phi flight partial Var-epsilon 2 plus v stab Var-epsilon equals j Var-epsilon c dot t Var-epsilon plus 8t. Here, lambda represents modulation space curvature, v stab is a potential ensuring stability, j Var-epsilon dot t Var-epsilon represents source currents in modulation space, and ht is a harmonic driving term. The entropy-resolved resonance profile is sharp mathematical filter expressed as m of x dot e squared e lambda ex by e0, where fx is the raw field configuration, ev(x) measures resonance deviation from an attractor e0, and lambda is an entropy selectivity parameter. This double exponential form imposes an exceptionally strict selection, so only configurations near perfect resonance become stable particles, explaining the discrete nature of observed particle types. From these foundational elements emerge four fundamental dynamic processes governing particle behavior. 1. Information flow and coherence stabilization ensures quantum information encoded in the field maintains coherence across modulation and time, mathematically described as d1 equals alpha I frac d Var-epsilon dt t dot t Var-epsilon. 2. Baseline resonance stabilization establishes the fundamental oscillatory carrier wave within the modulation field. D2 equals A0 sin, frac x lambda var epsilon right. 3. Rotational modulation accounts for intrinsic angular momentum and spin by describing rotation or precession of the field. D3 equals Nabelheim's frac parcellon times phi. 4. Structured localization produces spatially localized, stable energetic structures interpreted as particles. D4 equals E where R, R0, R far, R. These four processes collectively generate and maintain stable particle configurations, determining fundamental properties such as mass, charge, and spin. For a particle to emerge as a stable entity, four interdependent conditions must be simultaneously satisfied. The metric compatibility condition requires the spacetime metric to support wave propagation with the particle's specific dispersion relation. The stabilization potential condition demands a potential supporting the particle's modulation profile as an eigenfunction. The source current condition necessitates source currents in modulation space matching the particle's resonant mode. The entropy-resolved resonance condition filters configurations to select stable, coherent particle patterns. Mathematically, a particle's field configuration decomposes into a spacetime wave function and a modulation profile. Phi text particle xt repsilon equals psi text particle xt cdox particle O. Both components satisfy coupled equations, reflecting the four emergence conditions. This framework enables reverse engineering of exact spacetime modulation configurations for specific particles. The paper applies this framework in detail to various fundamental particles, starting with the electron. The electron emerges as the simplest stable fermionic solution, represented as a wave packet in spacetime coupled with a Gaussian modulated profile in modulation space, including a half-angle phase factor that encodes its spinorial nature. Phi text electron xt var epsilon equals ne in dk equal ik.x in dvonga delta omega meskirt k2 plus me2 etherness I omega t ether alpha e var epsilon 2 alpha e var epsilon ether I theta 2. Here is a normalization constant. Alpha e relates to electron mass and fundamental constants, and H0 is the zeroth Hermite polynomial. The electron's modulation profile is confined by a stabilization potential that includes quadratic and quartic terms in var epsilon and its derivatives, forming a harmonic well in modulation space. V stab phi var epsilon equals alpha e 2 plus beta e phi square 4 plus gamma e left frac partial phi partial var epsilon right 2 plus kappa e var epsilon twad phi 2, with precisely determined coefficients ensuring stability. Spacetime conditions include a metric perturbation associated with the electron's mass, albeit extremely small, and a source current in modulation space that sustains the electron's oscillation pattern. The entropy selection condition filters to the electron's energy attractor, ensuring uniqueness and stability of the solution. Remarkably, the framework derives the electron's mass exactly from vacuum parameters such as vacuum energy density, modulation length scale, Planck's constant, and the speed of light, eliminating the need for parameter tuning. The derivation integrates kinetic rate modulation and stabilization energy terms to yield ME equal 9.193356 times 3, matching the measured value precisely. Similarly, the electron's elementary charge emerges from the phase structure of its modulation profile, formulated as a surface integral of the phase gradient in var epsilon space. This calculation yields the known elementary charge E equals 1.60217634 times 10 squared minus 19 text c exactly, explaining charge quantization as a natural consequence of field topology. The spin-half property arises from the half-angle phase term E square I theta 2, which requires a 4 pi rotation to return to the initial configuration, analogous to the topology of a Mobius strip embedded in combined spacetime modulation space. This topological interpretation provides a deeper foundation for spin than its usual postulation. All electron quantum numbers, principal, angular momentum, magnetic, and spin, emerge automatically from the modulation profile's structure, with values corresponding to the electron's ground state configuration. The framework also explains the electron's wave-particle duality. The full description requires both spacetime and modulation coordinates, but experimental observations project onto spacetime alone, producing wave-like or particle-like behavior depending on context. The localization radius corresponds to the electron's Compton wavelength, naturally reconciling its spatial extent and diffraction properties. The photon is treated as a fundamentally different resonance pattern, a massless spin-1 boson with a modulation profile involving the first Hermite polynomial H1 and an integer phase factor ether I theta, reflecting bosonic behavior. Phi text photon xt var epsilon equals n gamma int k ether I k dot x int d omega delta omega minus k eth beta I omega t ether beta gamma h1 skirt 2 beta gamma var epsilon vikir I epsilon is the polarization vector perpendicular to propagation. The photon stabilization differs from fermions by featuring a quartic dependence on var epsilon rather than quadratic, supporting bosonic solutions. Importantly, the odd nature of H1 ensures the integral overmodulation space vanishes, enforcing the photon's masslessness. Spacetime conditions for the photon include a metric compatible with massless propagation and a source current sustaining its oscillatory pattern. The entropy selection condition includes a constraint guaranteeing zero mass, setting the photon apart from massive bosons. Photon properties such as masslessness, two transverse polarization states, and spin-1 arise directly from the modulation profile and field equations. The framework derives gauge invariance as an emergent symmetry from the modulation profile structure, rather than imposing it axiomatically, explaining why electromagnetism exhibits gauge symmetry. Quarks are modeled as more complex fermionic structures with modulation profiles incorporating higher-order Hermite polynomials, notably H3, introducing a three-lobed structure in modulation space corresponding to the three color charges red, green, and blue. The field configuration for quarks includes terms phi text quark xt var epsilon equals nq int dk, either ik.x derm of omega k2 plus mq squared, eta minus omega t ether dash of alpha q var epsilon to 2 var epsilon plus cq h3 alpha epsilon, ether I theta 2. The fractional electric charges of quarks emerge from the phase structure in modulation space, with the winding number determined by the coefficient nq, taking values corresponding to up and down quarks, yielding charges plus 2/3 e and minus 1/3 e, respectively. Color charge arises from the SU3 symmetry embedded in the stabilization potential, which includes terms involving the generators TA of S3 and a coupling constant lambda c, producing triply degenerate solutions. Confinement, the empirical fact that isolated quarks are never observed, emerges as an energetic condition. The stabilization potential diverges at large spatial separation unless the sum of quark charges in a composite system equals 0 or PME, enforcing bound states such as baryons and mesons. Protons and neutrons are described as three quark bound states with their field configurations constructed as anti-symmetrized products of individual quark fields to ensure proper fermionic statistics. The proton mass is derived precisely as the sum of constituent quark masses plus binding energy, computed from vacuum parameters, the strong coupling constant, alpha s, and proton radius, yielding mp equals 1.6726219268 times 10⁻⁻27, matching the experimentally measured proton mass exactly. This derivation addresses the proton mass puzzle by analytically including binding energy contributions from the field equations, surpassing numerical lattice QCD approximations. The weak force carriers, the Z and W bosons, are modeled as massive spin-1 bosons with modulation profiles involving a mixture of the zeroth and second Hermite polynomials, ensuring a non-zero integral overmodulation space, which corresponds to their non-zero masses. Their modulation profiles are psi zeta var epsilon kappa z equals e to the minus beta z epsilon squared h gross squirt 2 beta zeta z h2 2 beta the I theta e to the I theta. The inclusion of kappa w equals e to the beta w var epsilon 2 h02 plus e to w h2 2 b var epsilon e to the I theta. The inclusion of h0 distinguishes these bosons from the photon and leads to their massiveness. The framework provides a principled explanation for the masses of these bosons, including the correct values measured experimentally. Moreover, the Weinberg angle theta w, which quantifies the mixing between electromagnetic and weak interactions, is derived as an integral over modulation space involving coupling kernels, yielding sin 2 theta w approx 0.23 in agreement with experimental observations. This derivation offers insight into electroweak unification from first principles rather than treating the Weinberg angle as an empirical parameter. The W boson mass is obtained from vacuum parameters and the Weinberg angle via a precise formula matching measurements, resolving tensions between theory and experiment. Interactions in the AMC framework arise naturally from coupling terms in the field equations expressed through a modulation coupling kernel K var epsilon 1 var epsilon 2 that controls interaction strengths and properties without introducing separate coupling constants. The kernel has a universal weighting function with coefficients Wn equals 0.602, 90.172, 0.205, 0.054, 0.19, and takes the form K var epsilon 1 var epsilon 2 equals sum n equals 1, 5 wn's left, frac 2 pi n, var epsilon 1, var epsilon plus r right. Electromagnetic interactions emerge from coupling between charged fermion fields and the photon field, reproducing the fine structure constant alpha with extraordinary precision. Alpha equal frac E2, 4 pi epsilon 0 bar C, equal frac 1, 4 pi, int d var epsilon score 1 d var epsilon 2 k e m 2 e var e gamma var epsilon 2, yielding alpha approx 7.273556292 times 10 to the minus 3. The strong nuclear interaction arises from coupling between quark and gluon fields, with the modulation kernel's nonlinear dependence on modulation coordinate separation reproducing asymptotic freedom and confinement behaviors characteristic of quantum chromodynamics. This offers a fundamental explanation for these properties beyond phenomenological models. The weak interaction emerges from couplings between fermions and W or Z bosons, exhibiting parity violation and flavor-changing properties naturally from the modulation coupling structure, extending electroweak theory by deriving interaction forms from first principles. The paper concludes by outlining several experimentally testable predictions that extend beyond the standard model. These include new particles corresponding to higher modulation modes with precisely derived masses, Mn equals frac 2 pi n bar C quad n bar 5. One predicted particle mass is approximately 7 TeV, offering specific targets for collider experiments. The framework also predicts particle decay rates linked directly to modulation resonance imbalances, connecting lifetimes to modulation profile stability. Gamma pro left, pro partial 2, psi part of var epsilon 2 plus kappa 2 plab v stab phi right 2. Additionally, high-energy collision signatures are expected to exhibit resonant enhancements at energies matching modulation modes, suggesting new data analysis strategies to detect subtle energy bumps. Precision tests suggested include measurements of particle mass ratios, searches for modulation resonances, refined coupling constant determinations, and detailed decay pattern analyses, providing clear benchmarks for verifying or falsifying the theory. In summary, the Auxiliary Modulation Coordinate framework fundamentally redefines particles as emergent spacetime modulation resonance patterns, deriving their properties from deterministic field dynamics without free parameters. It unifies fermions and bosons as different modulation modes, explains quantum numbers and statistics topologically, and accounts for interactions through a universal modulation coupling kernel. This approach not only resolves long-standing conceptual challenges, but makes precise, verifiable predictions, offering a profound new understanding of physical reality.